Again, welcome. We're here today to talk about the Geoid Slope Validation Survey of 2014. And what I'm going to do, if I can figure out, there we go. What I'm going to do is discuss sort of the premise behind the survey and the field work that took place in the survey. Jan will follow up with the results from that survey. So, as you would probably realize based on Christine's questions, is this has to do with the replacement of NGS's or of our nation's reference frames. Specifically, in this case, it's our vertical reference frame, or North American Vertical Date of 1988, and that really hinges on a project that we have underway called the GRAV-D survey. And the GRAV-D survey is a process of determining a very precise gravimetric model for the United States. So within our NGS, within our 10-year plan, that's the goals that we have, is that our new gravimetric geoid that would be used for defining the future vertical datum would have an accuracy of 1 centimeter. And as folks can imagine, it's a very laudable goal, and I think what this project, what the Geoid Slope Validation Survey project is designed to do is to determine whether or not we can actually achieve that goal. What we're attempting to do with GRAV-D is something that has really never been done before, at least certainly on this large of a scale and within the United States. So determining whether or not we've met those goals is extremely difficult and takes a significant amount of verification in order to determine that, and that's exactly what this survey was designed to do. So the goal for this survey would be to observe the shape of the geoid, or the slope specifically, using other methodologies, and in this case, these methodologies are tested methodologies. They've shown good results in the past as far as being able to determine geoid slope at a highly precise level, but they're also extremely time-intensive and labor-intensive in order to do. And so, as you can imagine, we certainly couldn't use these methods on a nationwide level in order to create our geoid model. The first is a combination of GPS and leveling, where we can obtain very accurate and precise GPS-derived ellipsoid heights and difference those with leveling-derived orthometric heights to give us geoidal values at locations, and also using deflections of the vertical, and we'll talk about that a little bit. We'll take then we would take the observed slopes from our terrestrial surveys and compare those to the model slopes from the GRAV-D survey, or I'm sorry, from the satellite gravimetry, and then look at the results, comparing both existing models and then those existing models with the addition of the GRAV-D data. So just a little cartoon that most folks are probably very familiar with and you've seen many, many times. But as we know, with GPS we can observe our ellipsoid height directly, and that's shown as a line that's perpendicular to the ellipsoidal surface. And then we also can observe our orthometric height, and that's the line that the information that we're getting relative to the geoid, or our sea level surface, if we want to think about it that way. And as we can see, we have a difference in the direction of those lines, and that direction that we see is called the deflection, or the difference of the two is called the deflection of the vertical. So one of the methodologies that are used to get the deflection of vertical is to do astronomic positioning, where we can look at the difference between an astronomic latitude and longitude and a geodetic latitude and longitude, which would be derived with GPS. And that difference would give us the deflection of the vertical, which shows us directly the direction, or the, I guess you'd say the direction of the gravity field or the geoid at that location. Just go through the rest of these. So why not use existing surveys? We could go in and we have leveling surveys throughout the country. We have GPS surveys throughout the country. Why not use those? Well, the reality is that most of the existing marks that are out there are not necessarily GPS or gravity friendly. If we want to go out and get current data, we would have to do observations on those marks. And as you know, if leveling marks or if level line goes through a valley or goes through an area where there's a lot of trees, then we wouldn't be able to do that, do the GPS work. The existing leveling that we have out there in most cases is quite old, so we'd be relying on old observations without any idea of the validity of the orthometric heights that are published on those stations. And again, along those same lines as the existing leveling, it's unaudited. So even if the leveling was good 20 or 30 years ago, we have no real idea whether or not the published heights would still be valid or not. And the overlap of existing gravity, GPS, or leveling is minimal in space, widely separated in time. So again, there's just a lot of as far as our existing data holdings, they certainly wouldn't suffice, and even existing marks in the field not necessarily suitable for doing new surveys on. So we needed to look for locations where we could create the type of survey or create the survey line that we wanted to in order to support this project. So some of the criteria that we needed to have was that the project area needed to be quite extensive, significantly exceeding 100 kilometers. In most cases, it was about 300 kilometers, as we'll see. We needed to have existing GRAV-D data, so existing airborne gravity, or that area where we were going to concentrate this project would be scheduled to have data being taken very soon or very in the same proximity or same time frame as when we were going to be doing this project. Obviously, for GPS purposes, we needed to avoid areas where we had trees and woods and obstructions that would create issues with GPS data collection. We needed to be along major roads so that we had easy access to highways and ample room to work within. Cloud-free nights, very important for the astronomic work. The astronomic work takes place at night. So if it's cloudy every night, you don't do any observations. So a significant amount of planning went into looking at two locations where we could expect to have a large number of nice starry nights. No significant bridges along the route for leveling. Anybody who's done leveling knows that leveling across bridge spans can create problems if you have traffic on those spans. So we intentionally tried to stay away from any place that had long river crossings or valley crossings where bridges would be an issue. For the at least initially, we're looking at low elevations and fairly flat, so that would be easy to work within for leveling and for the other techniques we were using. Also looking for an area that may have some significant geoid slope. So if we're trying to model something that's not changing, then it's probably pretty easy to do. So we were looking for areas that had a challenging geoid surface, if you will, in order to better determine whether or not we were meeting our goal of that 1 centimeter. And also, economics comes into play too, because we have a limited amount of money within our budget to do these projects, and this was going to be an expensive project. We really needed to look for areas where our travel could be minimized, if at all possible. So, excuse me, GSVS 14 that we're here to talk about today was actually the second project in a series of 3 that have been planned. The first one was done in 2011 in Texas. You can see there we had about 325 kilometers, went from Austin down to the coast, Rockport area, Corpus Christi. If anybody can remember, in 2011 it was extremely hot. We had daytime temperatures that were ranging in the 100 plus degree range. They had a major drought during that time period. Excuse me. And so for the crews that were operating during the day, that was quite difficult conditions to work in. If you can imagine doing geodetic leveling in the sunny skies of Texas when it's 105, 160. 2000 was in central Iowa. I went from Denison to Cedar Rapids, and although fortunately our crews weren't affected, if anybody can remember 2014, there were a significant number of tornadoes and severe storms and flooding events that took place during that summer, and fortunately it did not severely or significantly affect our project operations. So as I indicated, we had a number of different techniques that were being used. One of those was campaign-style GPS. So we had a significant number of GPS receivers that were operating. We'll talk about that configuration, but excuse me, marks were set in the field over that distance. If I go back for a minute, we can take a look. We're looking at about 330 kilometers, so 205 stations along that route, spaced at approximately every mile or so, every mile to mile and a half. Marks were set. They were set in locations that were going to be suitable for doing GPS and doing leveling. The DOV work could be done on an eccentric location, so maybe on the shoulder of the road as opposed to out in the grass itself. Prior to the survey, all of the GPS equipment was verified. They did a recalibration of the antennas that NGS had. They physically measured every fixed height tripod that we used on the survey, both before and after the survey, and that's the graph you see to the right. We had 20 complete sets of equipment, varying different receivers, but every antenna was with the exact same antenna model. That was done intentionally to try to minimize any differences that might exist in the antenna calibrations between different manufacturers or different antennas. We had each party observed 5 new and 5 repeat stations every day, so they sort of moved along the highway, sort of like I think as our party chief described it, sort of like an inchworm. So the crews would move ahead. The five stations sort of overlap the next ones and would continue on. They had a total number of 30 observation days to get work done, and the project was processed using NGS's Opus project software. Geodetic leveling, we conducted first order class 2 geodetic leveling over the entire route, hitting all of those marks. We used, I think we had 2 geodetic leveling crews out there at the same time. And here you can see and get an idea of that operation. I'm sure many of you have seen that before as well. We had, for the geodetic leveling, 2 crews of 4 to 5 people in each crew. First order class 2, 749 kilometers combined of leveling for a total of 105 crew days, and 7.1 kilometers per day per crew. So as you can see, they moved along at a pretty good rate, and fortunately, again, as I indicated, weather didn't severely hamper our operations. Gravity observations. So we had a number of different gravity observation techniques that were used. We had 3 first order class 2 absolute stations located at the east and west sides of the line, so Denison and Cedar Rapids on the ends, and then at Ames in the center. Conducted A10 absolute observations on every 7th station. So this is it's an absolute gravimeter, unlike what we saw here. This is the high-end, non-portable, if you will, absolute gravimeter. The A10 is much more portable and can actually be used in a field setting, field environment. So we actually had some of these survey stations. Every 7th station was observed using an absolute method with the A10. Gravity gradients were taken also on every 7th station, as well as at the, I'm sure that they were taken at the tie stations at the east, west, and center. And also relative gravity observations on every official mark along that stretch. So excuse me, for the relative gravity observations, 10 stations were done per day, and it needed 23 days to make those observations. So here we see the absolute gravimeter set up indoors, and this has to be in a climate-controlled environment and in a building where we don't have a lot of people coming in and out. And so these were actually, I think we've done primarily. I think we used some schools and a college, local community college, and it was done in the summer, so school was out of session. So it was a quiet and secure environment to set these up, and they would run, I believe, somebody in the room in Silver Spring could probably collect me, but I think that these ran at least over a weekend and potentially even more. Here's an image that shows one of our relative gravity instruments set up on one of the observations in the field, and as you can see, the size of the concrete survey mark is quite a bit larger than what we would normally see, and these were specifically built in this manner so that we could do these observations. The relative instrument needs to have a flat, hard, and stable surface to operate on, and the A10 takes up just about the entire footprint of that concrete monument. So that's why we created a large monument that would support those observations. This is an image that shows the gravity gradients that are done, and so essentially relative observations are taken at these locations, or using the relative, I believe that just the same relative gravimeters, but they're actually taken at specified heights above the survey mark itself. So in that sense, you can get a gradient of gravity at that location. And then the deflections of the vertical were done, and this image shows what that was. This is an instrument that we borrowed from University ETH in Switzerland. They designed this machine for doing astronomical observations, and they've written the software along with a collaborator of theirs who wrote the star extraction software. And this instrument works essentially by taking images of the star field, multiple images of the star field, and then using an almanac, you can determine your astronomic latitude and longitude at that location, and that can be compared with the geodetic latitude and longitude that came from the precise GPS observations that was done in the campaign GPS survey. And again, the difference between the astronomic and geodetic latitudes and longitudes would give a direct indication as to the direction of gravity at that location. The DOV survey, we had 200, excuse me, actually it's not 228 stations, it was 228 observations. We did the 204 official points. We made 11 redundant observations for quality control purposes, and we had 3 re-observations that we conducted. This took place over 31 actual nights in the field. I think we had 40 some odd nights that we tried to work, but due to clouds or rain or a busted setup, because sometimes we had on the west side of the line we had significant train traffic, which as you can imagine with instrumentation as sensitive as some of this, it would cause vibrations in the ground. Even sometimes if you couldn't feel those vibrations, the vibrations affected the observations. So sometimes those observations would have to be redone. And again, we observed using the Swiss Kodiak astrometric camera. And I think that's the end of the description of the field work, and I'll turn it over to Jan to talk about the results.